Hello guys, welcome back to my channel Gamma Di Gamma. So in the last video we talked about orthonormal coordinate systems, not just orthogonal. So please watch that video before coming to this one, because this one we're going to do some differential geometry and we're going to look at how operators look like in this notion of a general curvilinear system, which is again orthonormal. So please watch that video, because this video won't make any sense if you don't watch that one. Okay, so let's get started. Okay, so here I have briefly drawn a differential element of this general curvilinear system. So we describe what a general curvilinear system would be. It would have free variables q1, q2, q3 with these respective basis vectors q1 hat, q2 hat and q3 hat. That's what I've drawn. I've just drawn what a differential, in this case volume element, looks like when your axes are just your basis vectors. So in the Cartesian system, if you recall, if you had, say, I don't know, Ez hat, Ex hat, Ey hat, your differential element would just be that cube. But in this case, there is no obligation for this figure to actually be a cube, because if you think of this in terms of these scaling factors, you remember our the basis vectors that we had, say, I don't know, qi hat was defined as partial derivative of the position vector with respect to that coordinates multiplied by 1 over the scaling factor for that variable. So we have this length, this extra length factor, and that length factor, as I demonstrated in the last video, depends from point to point. So if we take this as the reference point, then this length is going to be h1, or the scaling factor evaluated at that reference point. And since this is a differential, this is in the limit that this distance between them goes to 0, we can clearly define it using this 1 point. And so instead of just having a dx like we would here, we have dq1 but multiplied by the scaling factor evaluated at that reference point. Okay, so if we look at the top face, we have this point of the top face is q1, q2, q3 plus dq3, which is exactly like we would expect in the Cartesian differential element. You just increment by that amount in that direction. So in this case, this point would just be x, y, z plus dz. So although both of them are, you don't need a scaling factor for the dq, because basically those points are like on top of each other, but the length or the path that's connecting those points is not straight. So to account for this non-straightness, we have this scaling factor for the length, because it's a curvilinear system, right? The paths won't be straight necessarily. So again, so if you have this reference point if you want this distance, you take the scaling factor evaluated at that original reference point, because we're no longer on this face, we're on the top face, so this is the new reference point. That scaling factor evaluated at that reference point multiplied by this dq2 term, because of course we're along that axis, this q2 hat axis. So if you look at this, we can draw analogies. We can see that d tau, our differential volume, which is just a number, so this number should agree from one coordinate system to another, because it's just a number. This is equal to, well, in a Cartesian system it's like dx, dy, dz, right? But in this case, all of these guys individually, because I proved in the last video that, say, dr, your differential length element, is dqi hi evaluated at, say, q1, q2, q3, qi hat. So just taking the magnitude of this, you just lose the qi hat, you get these guys, so all these dq's along with their scaling factors. So we can see there's a direct correlation between them. So this Cartesian volume element is just dq1, dq2, dq3, h1, h2, h3, where you evaluate all of these guys at q1, q2, q3, because according to this figure that was our original reference point. And again, if this is inside an integral, this reference point will change because this is a function of the variable of integration. So you're sort of covering each and every reference point. That's the way of thinking about this. Now you do a similar thing for the differential surface area element, but we need to again obey the condition of orientation. So if it's the bottom or the top, so if it's the bottom, for example, which is like saying we have this bottom face here, then we would have a negative, because if you do the cross product again, because remember last video I said q1, q2, q3 are in right-handed order, which means if you do a cross product between consecutive terms, you get the other term with a positive. We don't get a negative. So that was important because of this definition of the surface area vector. So if you do the bottom, on the bottom you're in the q1, q2 plane. So those area factors are going to be dq1, dq2, but again, similar to this analogy of the differential say line element, we're gonna have to multiply by these scaling factors. But since this is a vector, remember that q1 hat crossed with q2 hat, at least for this guy, more like q2 hat crossed with q1 hat, because that's the way we'll define the orientation for this guy, because the normal vector will be pointing in the negative q3 hat direction, which is like this. So we get a q3 hat just because of the definition of orientation. But again, evaluate that at q1, q2, q3, because the scaling factor depends from point to point. So does this basis vector, because remember our bases are now space invariant. So are space variant. So they will depend on what point you are in space. That's why this idea of locality comes in. If you watch the last video of defining your basis vectors by these sort of partial derivatives. just because of the space variance of these basis vectors. And for the top, you have the same thing, h1, h2. No, we have a positive because the the orientation is like sort of positive q3 hat on top. But since we are on at the top face, the reference point is now this. So evaluate that at q1, q2, q3 plus dq3. You can repeat this process for any face, any two faces. So this right face or this left face or whatever. Okay. Now again, just to repeat this differential position vector. So if you differentiate position vector, you find the infinitesimal change, instantaneous change in the position vector. That's the better way of putting it. You can break it up using the chain rule here. Notice this guy is just the definition of the basis vector in our new general curvilinear systems, but we are missing a scaling factor, so multiply by the scaling factor. So I had covered this in the last video. I'm just recapping this. This establishes, and dr hat can be represented as say dxi ei hat. This is the Cartesian system. Whenever I have ei, those are the standard basis vectors, and therefore it's the Cartesian system. We also have this property that qi dotted with qj is equal to Kronecker delta ij. This is only because we chose our coordinate system, our general curvilinear system, to be orthonormal. And that was the role of the scaling factors, basically, to normalize everything. And a cross b can be, if you express a in this general curvilinear system, you have this expression crossed with, say, bj, qj hat, and ai is the component of a in this new system, bj is the component of b in this new system. Those components may not be exactly the same as the Cartesian components, because it's again an entirely new system. So we have ai bj epsilon I j k qk hat, only because this is a right-handed system, so we want this to work. Okay, this was a little recap and a little explanation into what this entire thing is here. Moving on to integral operators, line integrals, surface integrals, and volume integrals. We discussed these differential elements, but it's now time to basically sort of combine them with an integral. Okay, so let's talk about line integrals first. So for line integrals, say you have some curve in space, and a curve is like a geometric quantity. It should be, like vectors, independent of bases or coordinate systems, and you have some vector field v. So line integral is defined like this. Now we know what this differential line element is in our new general curvilinear system. It's going to be, say, dqj, scaling factor hj, qj hat. Fine. We can also express v in this general curvilinear system, because why not? It's just a system. So we have vi, say, qi hat, dotted with dqj hj qj hat. Now the dot product of these two basis vectors will give you a Kronecker delta ij, and when you contract over each of the indices, we can change the j's to i's. So we have, say, dqi hi vi. So notice we have a scaling factor in contradiction to our line integral. Say if we were to do this in like the Cartesian system, in which case we would just have, say, just this. Again, we would have to parameterize a curve differently, but that's another question. And I'm not taking the scaling factor outside, because remember what I said, scaling factor is point specific, so it changes from point to point, and so it's not a constant that you can just pull it out. I mean, unless you define your general curvilinear system to just be a scaled up version of the Cartesian system, then yes, we would have to pull it outside, because it would be a constant in that case, not in general cases. Okay, this was the line integral. Okay, moving on to the next idea of surface integrals, which are usually a little more cumbersome than line integrals or volume integrals, because we have this area or orientation dependence, which is stark evident every time we do them. So if you have your surface integral defined this way, where d sigma is your surface area, infinitesimal surface area vector, so you dot that with your vector field. And so assuming you have some, which is again assuming you have some surface in three-dimensional space. So we don't know if the surface is just in like one plane or two planes. So what we can do in the most general representation of this is have a plus and minus dq1, dq2, h1, h2, v3, because for face which is in the q1, q2 plane, area vector will be in the q3 direction, so you dot that the q3 with this vector v, so you get the v3 component out. And then plus and minus, because we don't know if this is just in one plane. Let's do another plane, the q2 q3 plane. So that will be similarly dq2 dq3, h2 h3, this time v1, because clearly the area vector will be pointing in the v1 direction, the q1 hat direction. And then plus and minus the last face, q1 q3, so dq1 dq3, h1 h3, but v2, because the area vector is in that direction. So this is the most general representation for this surface integral operator, because again we don't know if your surface is purely in one plane or is in a sort of in like in between two planes, or in all three planes in some parts, or we don't know. These things are complicated, so we have to generalize it in this way. Again, plus and minus, because we don't know what face we are dealing with, what's the orientation. And again, I'm not pulling the h1 h2s or any of these scaling factors out, because they're dependent on the point. So they're going to be like variables of integration. They're going to be like some functions of q1, q2, and q3. Okay, last order of business, volume integrals, which are pretty easy compared to these surface integrals. So assuming you have some volume in a three-dimensional space, call it this capital V, and assuming you have some scalar field, say rho of r, which you want to basically integrate over the volume d tau. Consider this like a density function. So this will be h1 h2 h3 rho of now q1, q2, q3, because we are integrating in the general curvilinear system, and then those differentials dq1, dq2 and dq3. Again, I'd explained what the d tau changes to, so this is just a recap of that. And since this is a scalar, we don't need to worry about orientation or direction. So there we go. That's how we do volume integrals in the general curvilinear system. Moving on to some differential operators now. See you on a fresh page. Okay, hey, so talking of gradients now, first in differential operators, consider a change in phi, d phi, and we define this. We actually showed that this was equal to the gradient of phi dotted with this differential position vector. Fine, we can express the position vector differential in the curvilinear system, so dqj hj qj hat, and we can use the chain rule on this side to get partial phi with respect to, say, qi dqi, gradient of phi dotted with dqj hj qj hat. Now if you analyze both sides of the equation, for the equation to be true, we want gradient of phi to be 1 over hi times partial phi partial qi hat. So if you plug this in, do the dot product, you will see that those scaling factors cancel off and you precisely end up with this left hand side. So this is the gradient in your general curvilinear system. Let me remind you, the gradient in the Cartesian system is simple. It's just, say, partial phi partial xi ei hat. Here you're not only differentiating with respect to those free variables, but you also are dividing by the scaling factor of that corresponding variable. And since this is going to be a sum, because we have subscripts here, these scaling factors will change depending on whether you have q1, q2 or q3. So that's just important to keep in mind. We also have these scaling factors. That's what's different about this curvilinear system, which is a general case. Now when we move to the divergence, the divergence is a little tricky compared to the gradient, which was like direct. It was straightforward, just use the chain rule, get the answer. For the gradient, we need to use this definition. Sorry, the divergence, we need to use the definition. Limit as surface and volume go to 0 of closed surface integral over some surface S as going to 0 of some vector field A dotted with, again, the area vector, divided by volume integral of a volume that's going to 0 d tau. So this was the definition of the divergence. If you don't remember this, don't believe me, just watch the video on the differential operator. This will make sense. Or even, watch Gauss's divergence theorem for that matter. It'll make more sense then. So the way we're going to actually do this is actually solve for the surface integral and the volume integral, and you get some form for the divergence. So let's do this. Let's be careful. Let's do this for, again, since this is a surface integral, we need to worry which surface is top, which surface is bottom, and the corresponding orientations and directions of those area normal vectors. So let's do this for bottom, the bottom face. So A dot d sigma is going to be negative because of the orientation. Normal vector is in the negative z3 hat, negative q3 hat direction. So dq1, dq2, h1, h2, a3, but this entire quantity that I'm bracketing, you evaluate that at q1, q2, q3, because that was your reference point here, just this guy. And again, a3 evaluated too, because it's a vector is a vector field, so each component is a function, so you need to take into account that dependence there. For the top face, a dot d sigma, we just have the positive sign, dq1, dq2, h1, h2, a3, evaluated now at this top reference point, because we are on the top face, which will now be q1, q2, q3 plus dq3. And if you want to see the pattern clearly that we are approaching, do this for not just top and bottom, but for all faces, the left and right, front and back. So, but what's important is clubbing these two terms, because notice this pattern h1, h2, a3 evaluated at say q1, q2, q3 plus dq3, which is basically this guy, is just equal to the first guy h1, h2, a3 evaluated at q1, q2, q3 plus partial h1, h2, a3 with respect to q3 evaluated at q1, q2, q3 times dq3. You can think of this as the first term of the Taylor series, or the definition of the first order partial derivative with respect to q3. And again, we can only do this because it's a differential volume element, so all these lengths, dq3 is basically going to 0, it's in that limit, so all these dq's, they're all going to 0. That's why we can do this kind of substitution. So if you club the top and bottom surface integrals, a dot d sigma, we can use this expression to just get partial h1, h2, a3, because we'll naturally have a negative sign, so that's like taking this and this term on one side, partial q3, dq1, dq2, dq3. Fair enough, fine. And if we do this for all the surfaces, this was for top and bottom, if we do left and right and front and back, the entire surface, closed surface integral, will just simply be a collection of these partial terms. So partial say h2, h3, a1 respect to q1, partial h1, h3, a2, q2 plus partial h1, h2, h3, partial q3, but all of this is multiplied by dq1, dq2, dq3, because you get those straight terms out. So you notice a general pattern for the top part of this definition. The bottom part, volume integral say d tau of this differential volume element, is simple. You just use the definition of that. It's going to be h1, h2, h3, dq1, dq2, dq3. And we don't need to add any like dependencies here, because we integrated over everything now. And again, even if you want to add those dependencies, we can do them like right here. We could have done the same here as well. it's mathematically healthy to add these dependencies, because again, this volume is a volume that's tending to zero, so better to add them. And you notice that if you plug this all into your formula, that these terms, these dq terms, will all cancel out. So all you're left with is just 1 over h1, h2, h3, and then these bunch of partials, h2, h3, a1, q1, partial h1, h3, a2, q2, h1, h2, a3, q3. So yup, that is your form for your divergence of some vector field A in a general curvilinear system. We can adopt a similar approach to find the curl. In case you guessed it, we used this definition, which was a sort of a function of Gauss's divergence theorem. We are going to use Stokes's theorem for the curl in this general system. So as I did for the divergence, I'm going to do for the curl. Notice, or remember this definition, curl of A was limit as some loop, some surface both go to 0, closed loop integral of A dot dr divided by surface integral of, say, just d sigma itself. Okay, now here let's consider some closed loop. Maybe let's take this first face, this face that has its normal area vector in the negative q1 hat direction. So let me just briefly, again, apologize for my bad drawing here, but just want to prove a point. See this face here. So this point is q1, q2, q3, the main reference point. This point will just be q1, q2, q3 plus dq3, and then this length is just h2 evaluated at this point. These reference points are important, as I said. This length is h2 evaluated at q1, q2, and q3, the bottom reference point. And the way we're going to do this is, so this first guy is like CA, this path is CB, this CC, and this CD. So we're going to integrate, we're going to do a closed loop integral on this face, and then we're going to generalize this idea for many number of faces, because then we'll just notice a pattern. So we have closed loop integral A dot dr is just equal to, say, CA dq2 h2a2, because we are in this in the q2 hat direction, so the dot product will just give components with the subscript 2. CB, we're in the q3 hat direction, so all the subscript 3 components. CC, again q2 hat direction. CD, q3 hat direction. But all we need to keep into account is those points, the reference points, and the orientations, if it's positive or negative. So for CA, so CA dq2 h2a2 is just h2a2, because this is a differential, so this guy will remain a constant evaluated at q1, q2, q3. This will remain a constant before this differential length. Don't forget the dq2, that's popping out basically. Do this for CC dq2 h2 a2. We will just have negative because we're going in the opposite direction to CA, for example. If you define that as positive, this will be negative naturally. You'll have q1 q2 q3 plus dq3. And again, I would also like to point out that the orientation we had for Cartesian system is again obeyed here. So clockwise is positive orientation, because clockwise will yield a surface area vector that's in the positive direction. Okay, club these two again, because notice h2a2 at q1 q2 q3 plus dq3 is just going to be h2a2 like before at q1 q2 q3 plus partial h2a2 q3 with respect to q3 evaluated at q1 q2 q3 dq3. And if you plug that in, you notice a pattern for all of those guys. This was just for say A and C. You do this for B and D. You notice the closed loop integral A dot dr is just going to be partial h3 a3 with respect to q2 minus partial h2 a2 with respect to q3 dq2 dq3. This was just for a loop in this I believe q2 q3 plane. If we do this for loops which are in all the planes, you notice a pattern that's going on, because this is clearly, again, let me just break everything down. I wouldn't want to skip any steps. This we know for this loop at least is h2 h3 dq2 dq3. So just for this, the first component of the curl of A in the general curvilinear system is 1 over h2 h3. You divide by this guy basically, times, there's no equal, partial h3 a3 over partial q2 minus partial h2 a2 with respect to q3. So that's the first component of the curl, because notice the area vector is in the q1 hat direction, so it makes sense for a curl to have the 1, because again, using this formula, the curl is just the line, the closed loop integral of A is just curl of A, surface area of the curl of A over the surface enclosed. So we anyways have to do the dot product with that normal element. So if we have the first component of the curl, which means the normal area vector is in the q1 hat direction, otherwise we wouldn't get that first component like that in that surface integral. Again, too many words, but you do this for loops in all planes. You notice a pattern. You notice that the curl of A in your curvilinear system generally is h1 h2 h3 in the denominator, scaling factors. You have h1 q1 hat, h2 q2 hat, h3 q3 hat, partial with respect to q1, partial with respect to q2, partial with respect to q3, h1 a1 h2 a2 h3 a3. And this is, when I write this as a matrix, this is basically take the determinant of this guy and multiply by this scaling factor triplet in the denominator. So the curl of A using subscript summation can also be expressed as epsilon I jk, or say h hjhk, partial, I believe, hk ak, partial qi. This is qj, qi hat. I believe this is right, but I hope you get the general idea of what this is. So if you notice all these divergence and curl, they have the scaling factors inside the differential. So this, again, you can't pull them out of the differential because again these are variables. So this means you can either write this as a product rule, but I just choose to keep it like this because this is nice. In the next video, hopefully I might try to give specific examples of using this method or of this general method, and then specializing it for spherical system and cylindrical system. So stay tuned for that. That's going to be way more insightful, way more helpful, because you'll clearly see that the reason I drew curves for this was not arbitrary, because if you do this in, say, spherical, you get these wedges, you get these differential wedges because it's a differential d theta factor. So yeah, I think that's it for this video. I hope you enjoyed this. Till next time, please like, share and subscribe to my channel, guys. Recommend it to your friends. Spread the word of gamma digamma in the math community. In the meantime, stay tuned for more content and stay safe. Peace out.